Hi folks, this is Shefik. Today we are going to implement Edwards curve digital signage algorithm, or shortly EdDSA, in Python from scratch. But before we begin, please like the video and do not forget to subscribe to the channel to stay up to date with the latest videos. Also, your comments are more than welcome. Thank you for your all support in advance. With elliptic curve cryptography, we are able to sign messages much faster than RSA, DCA, or aljamal. Herein, Edwards curves are special form of elliptic curves. It comes with simpler addition formulas than elliptic curves in Weierstrass and Koblitz forms. Besides, Edwards curve digital signage algorithm offers slightly faster signatures than elliptic curve digital signature algorithm. Original EdDSA paper recommends using twisted Edwards curves, and twisted Edwards curves are looking like to roundabout circulation, and here you can find its addition formulas. If you wonder the math behind this addition formulas and its proof, I strongly recommend you to read this technical tutorial. I'm going to share its link in the description, but in this video we are going to adopt these formulas directly. Let's implement point addition formulas. I'm going to create a function definition, and function name is going to be at points, and it's going to get p and q as input arguments. Also, we are going to fit a and b pair from the curve equation, and also modulus p. Here p and q are going to be tuples. That's why we can access its x and y coordinate values as x1 y1 is going to be p, and x2 y2 is going to be q. Then x3 is going to be x1 times y2 plus y1 times x2 over 1 plus d times x1 x2 y1 y2, and y3 is going to be y1 times y2 minus a times x1 times x2 over 1 minus d times x1 times x2 times y1 times y2. Thereafter, this function is going to return x3 y3 tuple. Also, let's highlight the curve formula here. A times x squared plus y squared is equal to 1 plus d times x squared times y squared. This is the formula of twisted Edwards curve. This addition formula is defined on real numbers. On the other hand, we are going to work on finite fields. In other words, we have a modulus and we are going to work on integer numbers. This requires to make calculations for mod p for both left and right hand sides. In that way, we are able to move those denominators to numerators with switching the values with its multiplicative inverse values. Firstly, I'm going to find the mod p values for the numerators. Thereafter, I'm going to change the sign to multiplication, and finally find the multiplicative inverse values for the denominators. This is going to be power, find its -1 power for mod p. Similarly, do it for the second denominator, and this multiplication might be greater than the value of p. That's why I'm going to find the mod p value here. Besides, the original EdDSA paper explains ED25519. This is an elliptic curve signing algorithm using Edwards curve digital signage algorithm and curve 25519. This is a special curve and its arguments are predefined. For example, its modulus value is 2 to the power of 255 minus 19. Similarly, a value in the curve equation is going to be -1. Thereafter, the value is going to come from here, and as you can guess, this is defined on real numbers. We are going to convert this to integer. That's going to be numerator times multiplicative inverse of denominator, and we are going to find its -1 power for mod p, and this multiplication is going to be in modulus p. And let's see, Once curve arguments are defined, we are going to need a base point on that curve, and this is going to be base point G. And this is a special point on that curve too. And we are going to need the value of u, that's defined as 9. Thereafter, y value of base point is going to be u minus 1 over u plus 1. And this is a real number too. We are going to find the multiplicative inverse value of its denominator to find the value on the finite field. Y value of the base point is going to be u minus 1 times u plus 1, and we are going to find these values minus 1 power for mod p, and this multiplication might be greater than the value of p. That's why we are going to find the modulus p here. And let's see the y coordinate of the base point, and the predefined x coordinate of the base point can be copied from this blog post. I'm going to copy it directly. X value of the base point is going to be this. We can validate that this base point is on this predefined curve. In this equation, I'm going to replace x to gx, y to gy, percentage symbol for modulus, and check this is equal to the right hand side. As you can see, this returns true, so our base point is on the curve. We should run this validation in the addition formula. Here we are going to check x3 and y3 is on the curve, and also we are going to define the base point as g, and it's going to be a tuple of gx and gy. Now our curve is ready. Also we implement our addition formulas. Let's try some addition. I'm going to build a for loop for I in range from 0 to 20, and before this for loop I'm going to define a point h, and its initial value is going to be g itself. Thereafter I'm going to call addPoints function, and here I'm going to add base point g to point h. Also the arguments we need to fit are a, d and modulus p. This line is going to be point h itself, and let's print the point h. This is actually I plus 2g. Let's run them all. As you can see, this is 2g, this is 3g, and finally this is 21g. They are all on our predefined curve because this line is performed in the addition. This shows that our addition formula is working successfully. Now we are going to pick a large prime number k, and thereafter we are going to find k times base point g. Here k is going to be our private k, whereas k times g is going to be our public k. But calculating k times g one by one with a for loop similar to this is a cost operation, because we are going to pick a very large integer number for our private k. That's why we are going to adopt double and add method to find the k times g much faster than one by one, similar to this for loop. As you can see, time complexity of this operation is O n in the big O notation. On the other hand, time complexity of double and add method is going to be O log n. Here I'm going to define the double and add method. Definition, apply double and add method. We are going to pass a point on that curve, which is going to be q, and an integer number k. Also we are going to pass a, d values, and also modulus p. We are going to define a variable named addition point, and its initial value is going to be q itself, and at the end of this function we are going to return this addition point. Here we need to transform the integer k to binary. That's why I'm going to create another variable. K binary is going to be binary value of k. This is going to return something with 0 and b prefix. Thereafter it's going to return binary value. That's why I'm going to ignore the two letters. and I can do this but from index 2 to end of the string. Let's say binary value for a sample k as this. Here I'm going to build a for loop to walk over the bits one by one for I in range. It's not going to start from 0 index. I'm going to ignore the first one and start from the second index, from 1 to length of k binary, and current bit is going to be k binary and get its e2 e plus 1 index. In this iteration we are going to apply always doubling and call addPoints function here, and both p and q points are going to be addition point itself. This is going to be the addition point. And after doubling the point, if the current bit is equal to 1, thereafter we are going to add the base point to addition point. We are going to add base point q here. So we are able to calculate the k times q much faster than building a for loop with double and add method. Now we are going to generate our private key. That's why we are going to import the random module first, and private key is going to be random dot get random bits, and EdDSA requires 32-byte private key. That's why we are going to set this to 256. Once private key is generated, we are going to generate our public key, and public key is going to be, we are going to call apply double and add method, and base point is going to be g, and here the integer value k is going to be our private key, and we are going to put a d from the curve equation at modulus p, and finally we are not going to need this block anymore. I'm removing it and run all cells. Let's print our public and private key. Private key is going to be an integer value, and public key is going to be a point on our curve. As you can see, this is going to be our private key and this is going to be our public key. As you can see, if you have the private key, you can calculate the public key very fast with double and add method, but if you have just public key, it's hard to extract private key because you don't have a double and add method. Reverse of it, you have to build a for loop and check all values one by one. This is called elliptic curve discrete logarithm problem, and this makes elliptic curve cryptography safe and secure. Once our private and public key pair is ready, once they are generated, we are able to sign messages, and I'm going to create a function transform text to integer values, and it's going to expect a text as input argument. In this function we are going to find encoded text first, and this is going to be text.encode, and that's going to be UTF-8. Then we are going to find the hex value of this encoded text, and let's say this is hex underscore text. Finally we are going to return the integer value of this hex underscore text with value 16. Let's see, we call text to integer function, call hello world. This is going to return this integer value. We are also going to define a function for hashing purposes, and this is going to get message as input argument, and here we are going to import the hashtip library. In this function, actually we are going to feed the result of text to integer function to hashing function. That's why message is going to be integer here, and I'm going to find the string value of this integer message first, then encode it with UTF-8, and we are going to call hashlib dot the hashing algorithm. We are going to use SHA-256, and we are going to pass this encoded text. After we are going to call hex digest function, and similarly call integer function with value 16. This is going to be our hash value. Let's say this is my message. Now we are going to generate a random key R, but this is going to depend on message itself with hashing. I'm going to call hashing function and pass message as input. Then add message itself and find the hash value again. Finally, the value might be greater than our modulus p. That's why I'm going to find mod p. This is going to be our random key, and as you can see, random key is depending on the message itself. Then we are going to calculate our uppercase, and this is going to be a point on our curve, and I'm going to call apply double and add method, and I'm going to find the lowercase r times base point g and pass default arguments a, d, p. Then we are going to find another large integer, and this is going to be x coordinate of the r uppercase plus x coordinate of our public key plus message, and this is going to be greater than our modulus. That's why I'm going to find modulus p for calculating h. And finally we are going to find variable s, and this is going to be our lowercase plus h times private key. So our signature is going to be our uppercase and s pair. Once we sign our message, we are able to verify, and in verification side we are going to have the message itself, r and s pair, public key also, and also we are going to have the constants on our curve, which are a, d, and f, and also in the verification side we are going to have our base point g. In the verification side, Bob can calculate the value h because he knows r, he knows public key, also he knows the message. Then Bob is going to calculate two different points. First one is going to be p1, and this is going to be s times base point g. He already knows a, d, p parameters. Then he's going to calculate the second point p2, but to find the p2 he's going to call add points function, and he's going to add the point r, and also he's going to calculate the public key times h, and these adp arguments are going to be constant here for double and add method and also add points function. Here we are expecting that p1 and p2 should be same point. As you can see, they are same, so we can verify this as x coordinate of p1 must be equal to x coordinate of p2, and similarly y coordinate of p1 must be equal to y coordinate of p2. If this line is satisfied, then verification is done. Let's change our message. Instead of hello world, I'm going to write hello London, and my r and s pair is going to be changed. Thereafter I'm going to perform these lines. Still its signature can be verified. Now let's focus on how this algorithm is working. As you can remember, our s value is random integer r lowercase plus h times private key, and here to find the p1 we actually calculated the s times base point g. Let's replace this explanation instead of s, so p1 is going to be times base point g, and we can represent p1 as random integer r lowercase times base point g plus h times private key times base point g. R lowercase times g was r uppercase, as you can remember here, so we can replace r uppercase. Thereafter private key times base point g was our public key, and we can replace this to h times public key. And p2 calculation, we add the point r to h times public key. So this must be equal to P1. So we implemented Edwards curve digital signage algorithm, or shortly EdDSA, with Python from scratch in this video. Thank you all for watching and see you next time.